So Phil completed his DPhil in computational modelling of X-ray lasers in 1991 from the University of York, after which he held research positions in the University of York, Université Paris-Sud, and the Czech Institute of Physics. He then spent 10 years in the finance sector, designing and modelling approximately $2 billion of asset financings. He returned to academia via an MSc in Quaternary Science from the University of London in 2006 and joined the Open University in 2007, initially as a postdoctoral researcher on glacial interglacial cycles. Phil's main focus is the development of computationally efficient Earth system models with a particular focus on interdisciplinary model coupling applications, integrated assessment and uncertainty quantification. So aside from my inability to speak, Phil, thank you for joining us, and I'll pass over to you.
Cheers, thanks a lot. That's perfect. Made sense. I'll just share my screen straight away, I guess. Okay. So does that all appear?
Yeah, looks great.
So I'll talk a bit about a paper we had out last year, and with Pallavi, who I see Pallavi's in the audience. I think Pallavi was the one who put my name forward for this talk. Thanks to her. I hadn't found out until today. But this started with an MSc student, in fact, two MSc students, Cecile Portier and James Thompson. And we were just looking at, what are the different drivers of Asian monsoons and running simulations to do it. So a bit of a background of the Asian monsoon, as I'm sure most of you are familiar. When you go into northern summer, you get heating of the northern hemisphere. So the ITCZ, the intertropical convergence zone, moves northward into the northern hemisphere, especially over land, because you've got this low heat capacity over land. So you get this big shift to the ITCZ. So you get winds that come in off the Indian Ocean, and they're very wet and they're warm. So as they come into the land, and they release their precipitation, hit the Himalayas, and start rising. And as they rise, they release more and more precipitation. And as they release precipitation, this is giving off latent heat, and this sort of pumps the whole system. So that's the kind of basic mechanics of what happens in the Asian monsoon. And the question we're looking at was, how's the Asian monsoon changed over time? What things have changed? Okay. So going back on paleo timescales, or in fact, you don't need to go on paleo timescales, on any timescales, whether it's daily, seasonal, annual, decadal, through to multi-million timescales, there are different drivers that affect the monsoon system. We're mainly interested here in paleo timescales, so these longer timescales where we're looking at changes to the underlying surface. So that's things like the sea and land distribution, the orography, the ice sheets, changes in sea surface temperature. And these things change the monsoon on a very wide range of timescales, going out to tens, hundreds of millions of years even. And then we're also interested in the distribution of the solar energy on the Earth and the heating of the Earth. So that's affected by orbital cycles, and greenhouse gases have an effect on that. And lots of paleo studies have looked at how the monsoon has varied through various stages in paleo history. And there have been many, many different drivers of variability. So there's a kind of few listed on the sheet here. So the effects of precession, so that changes the sort of heat distribution, where is the summer dominant, the amount of heating in summer. Greenhouse gases, they put more energy into the systems, they tend to pump a stronger monsoon. The uplift of the Himalaya and the Tibetan plateau is very important. So as I mentioned, when this moisture there hits the mountains and rises up, this is a big driver of the system. And then there's orbital forcing for obliquity as well. Ice sheets have an effect of shifting the ITCZ. And anything else on there? Oh, we've got Dansgaard-Oeschger events and Heinrich events. So that's changes to the AMOC. Again, they would change the sort of hemisphere energy balance and also affect where the ITCZ is sitting. So all of these different things are going on. How can you disentangle their roles? How can you look at interactions between them? So modelling is of course one way forward to sort of address those sort of problems. In a fairly recent paper, 2019, Farnsworth, they looked at the monsoon, the East Asian monsoon over the last 150 million years or so, and they sort of set up a around 30 or 40 sets of boundary conditions, so looking at detailed paleogeography, and they also varied CO2, and they performed 100 or so simulations with HADCM3 climate model that you're probably familiar with. And their kind of headline conclusion from that work was that it's the paleogeography that's driving the East Asian monsoon and not the CO2. So that's great. That's looking at one part of the question, but we were then thinking, okay, how can we address all of the different drivers together? So all the sorts of things that I was talking about on that previous page. And the model we use to do this is Plasm Genie. So the sort of minimum dynamics you need to model monsoon is you need to have a dynamic atmosphere, 3D dynamic atmosphere, and you need a 3D dynamic ocean. They're the kind of two main ingredients, because the whole thing is driven by that atmosphere-ocean interaction and the 3D dynamics of Hadley cells and what have you. So you need a model that's got those ingredients. But if you're looking at very long timescales, you also want a model that's quite fast. So Plasm Genie is quite well suited to this problem, this sort of question. It runs about 4 years an hour, and it spins up fairly quickly. So you can do a spin up in about 10 days or so. So a spin up is just when you set the model running and it finds its steady climate state. So that gives us the ability to sort of explore these problems in reasonable time, CPU time. Okay. So what's different about Plasm Genie? Where does it sort of sit on the hierarchy of models? So it sort of sits in this intermediate zone of intermediate complexity models that have a dynamic atmosphere. So that's the kind of models that have a dynamic atmosphere, famous Speedo, Usovic, Plasm Genie. They kind of take about a month to do a simulation. And these are all of the right sort of complexities to do this problem. If you go the other direction, you got towards HADCM3 and far beyond HADCM3, you're looking at much more expensive simulators. Obviously they have higher resolution and more complexity in the simulation, so they can capture more details, which can be very important, especially for questions like the monsoon, where the resolution can be key. And going in the other direction, you can move towards the reduced dynamical complexity. So models that just have very simple one-layer atmospheres, for instance, but those would be inappropriate for this problem because they don't have the dynamics that are necessary. So we're kind of in this sort of sweet spot of the sort of minimum adequate model to look at the model, you could say. So we can run with this gearing, which I won't talk about. We can run a simulation in a day. So given the fact that we're acknowledging it's the minimum adequate model, does it do a reasonable job of simulating the monsoon? So on the left-hand panels, you can see the modern day climatology. There's Plasm Genie on the left and reanalysis NCEP on the right. So you've got the June, July, August precipitation, December, January, February precipitation. You can see that Plasm Genie, although you could quibble about some of the details, it's doing a pretty good job of capturing the precipitation changes over Asia, over India and Southeast Asia. And then a little bit more detail on the right-hand side. So this is this kind of spatiotemporal development of the precipitation. So the x-axis is time, so it's just following through an annual cycle, January through to December. And then the y-axis, it's latitude, so looking from 20 south to 30 north, and this is a kind of shot over the Asian subcontinent. So I think it's from 70 to 90 degrees east. And so you can see the precipitation sort of moving northwards, and when you get into June, July, August, you've got this kind of strong precipitation over, which is the monsoon signal. And you can see on the bottom, Plasm Genie is capturing that spatiotemporal evolution pretty well. So although we won't expect to capture a lot of the details that are often important for monsoon studies, we're capturing the kind of large-scale features that we can draw some conclusions from. Okay, so we talked first about that experiment, the HADCM3 experiment, which is kind of one way to approach the problem, where you just put in prescribed boundary conditions that correspond to points in time and see what happens, and you can get a lot of understanding out of that. And the other kind of typical way that you would do these sort of experiments is single parameter studies. So here, these are a bunch of different simulations where we take the modern day climate, and then the first one we reduce the orogeny, the mountains, by 50%. We drop them all to their 50% of their height. Then we do another one where there's doubled CO2, another one where we put ice sheets in, one where the Panama is open, one with precession reversal, and all those sort of single parameter studies are giving you some idea about how these different things will affect the monsoon system. And you can already see that by dropping the orogeny, you get a big reduction in precipitations, which is especially clear over Southeast Asia. Doubling CO2, you get a strengthening of precipitation, especially over India, and likewise. So you're pulling a lot of information out of those. On the bottom, I just put that in because we didn't look at the solar constant, and it was something we could have included. So the solar constant has reduced by about 3.5 watts per meter squared. Actually, that's something I mentioned. We're looking over the last 30 million years in this study. That's the kind of time frame that we're interested in. So over that period, the solar constant is reduced by about 3.5 watts per meter squared. So that does have an effect on the precipitation, on the monsoon precipitation. But you see, the scale it's about an order of magnitude less than the things we're focusing on above. So I'll just kind of mention that. And out of these sort of experiments, you can do lots of other things, looking at how different aspects of the system are changing. So obviously you can draw lots of physical understanding about what the responses are. So I've just happened to choose the AMOC, the Atlantic Meridional Overturning Circulation. So what happens to that in these different sensitivity experiments that are plotted up? So just as an example, because we'll come back to it later, the Panama, when you open up the Panama, you can see you get this salinity redistribution when you open up the Panama. So the Atlantic becomes far less saline, and the result of that is the overturning circulation collapses. You stop having an AMOC. And that can have kind of long teleconnections to things like the monsoon. So these sort of tools where you're running these simple single simulations give you a lot of understanding about what are the driving forces. Okay, sorry. And then there's another kind of interesting experiment that's worth mentioning, which kind of shows that this kind of resolution we're working at, we can get useful results out. So on the left-hand side, there's a simulation with the present day orogeny. And then in the center, there's a simulation where we flattened the Tibet Plateau, but we still leave the Himalayas in place. And on the right-hand side, we flatten the Himalayas, but leave the Tibetan Plateau in place. And you can see from this simulation, which has been seen elsewhere in very high resolution models who have looked at the same problem, that what's really important for the monsoon, the Asian monsoon, is the Himalayas. When you remove the Himalayas, the monsoon is hugely weakened, but if you remove the Tibet Plateau, it has very little effect on that precipitation field. So just a bit more background. But okay, we want to look at 30 million years. We want to look at all of these different things together. We want to look at the interaction between them. So our model still isn't fast enough for this. If we're running over 30 million years, that's hundreds of years of computing. And at the Open University, one of the tools we use a lot is something called emulation. So we use these baselines with our intermediate complexity Earth system models, which get us so far into problems. But when we go to emulation, it takes us many orders of magnitude faster in speed. And that gives us sort of two main categories of the work that we do. Some of it's interdisciplinary stuff, where we're looking at coupling climate models to other types of models. So looking at economics impacts, climate change impacts, and biogeographical models. And the other one is looking at the relationship between this high dimensional input space you have of models and high dimensional output space. And this is kind of for calibration and process understanding, which is the kind of problem that we're in here. So what is an emulator? I'll just summarize it schematically here. So on the top, you have your simulation, your Earth system model, or whatever model you might be running. And there's kind of the working components of that model are science. So you've got lots of physics or biology coded up into that model. You have a series of variable forcing inputs. So these are things like you might prescribe the CO2 concentration or the solar constant or the orbital forcing, what have you. These are kind of forcing inputs. And then you have parameter inputs. So parameters are numbers that you don't necessarily know in your model. So it might be perhaps the albedo of ice or something like that. You won't have a precise value for that. So there's the kind of two different types of input to the climate model. And then you get out this high dimensional output where you can look at huge amounts of model data over time, space, whatever variables you want to look at. But what does an emulator do? It captures all of that science by statistics. So it has these same variable forcing inputs. You can apply same variable forcing inputs to it. You can apply the same variable parameter inputs to it. But this emulator is now trained upon the simulator. So you run a bunch of simulations with your simulator, and you'd use that to just train a statistical model. And you're typically, with an emulator, you're looking at a reduced dimensional output. So you'll be looking at one or two variables, or perhaps, you know, one or two time slices. So you haven't got this ability to kind of pull apart the science that you do with a model. You don't have the ability to look at many different output fields as you do with a model. But what you do get in return for that is something that's very, very fast. So fractions of a second, something that would take days in the model itself. So yeah, I think I probably said that. It obviously does introduce some extra error. So you've got error due to the fact that you're emulating. It's not the simulator itself, but typically we would quantify that through things like cross-validation techniques, and you find typically that it's far less of an error than the model itself. So when you start quantifying the uncertainties in your model, you'll find they're very much greater than the models in your the errors in your emulator. And another big weakness of an emulator is that you can only train it, and you can only ever stay within that space you train. So you can't just build a model of 21st century climate change and then apply it to deep time paleoclimate, for instance. It's very has to be specifically trained on the question that you're looking at. Okay, so for this problem, looking at how the monsoon has varied over the last 30 million years, we need first of all to build a bunch of simulations to train our statistical model. So these boundary conditions, sorry, I don't know how noisy that building is outside. I hope it's not too bad. We vary the land sea mask, so there are 3 maps on the top. We've got the present day map going back 5 million years on the left. Then in the center, we've got a map with the Panama being open, which we say is between 5 and 15 million years ago. And on the right-hand side, we have the Panama open and the Tethys open. So these are kind of our 3 model states, our 3 world states, if you like. Huge implications to the changes that did happen over those times. So actually the Tethys was this very large land that was gradually shrinking. So we're not capturing all of the details of what, but we're capturing the first order effects of closing a Tethys, closing a Panama to end up with a modern day. Then we have some ice sheets. So that the map on the bottom left is the LGM glacier mask. So that's Peltier 5G. And we kind of use that as the basis to vary that over time. Big approximations in there, because assuming that, well, we don't just use the LGM glacier mask, we use all of the Peltier mask going back to the LGM 21,000 years ago, but we kind of map them against sea level. So we assume if the sea level was 50 meters lower at some point in the past, then we'll just use the Peltier mask that corresponds to 50 meters lower, even if it's 10 million years ago. Now, of course, many huge approximations involved in that assumption, but it's a start. And then we have orogeny. So we're not looking at lots of complex different types of orogeny. We just take the modern day map, that's the modern day orogeny, and we scale it by, I think, between 0.5 and 1 in the actual experiments. So 50% as a proxy for 30 million years ago. So we vary all of these things, all of these maps. We vary the orbit, so through the eccentricity, obliquity, and precession, spanning the solutions of the orbital solution. We vary CO2 concentration from 160 parts per million to 1500 parts per million. So all of these things, all these different options we have, we just vary them randomly. There's a bit of thought in the design of how we vary them randomly, but essentially you can think of it as a randomly varied bunch of boundary conditions. We just run the simulations, and we use that to train our emulator. So our emulator finds out what happens as we vary all these things and how these things interact with one another. And what do we emulate? Well, I was talking about reduced dimensionality. So we've got all this lovely complex stuff coming out of our climate model, but all we're going to look at is the annual precipitation over these 2 masks as our kind of proxy for the things that we want to see how that varies over time. So we've got a mask representing the Indian summer monsoon and a mask representing the Southeast Asian monsoon. We just take the average annual rainfall over those masks, and we see how that number varies as you vary all of these other inputs I discussed on the previous page. So what is an emulator? Won't go into any details about what an emulator is, but it's just a function. You don't really have to think of it any more than that. You can think of it as a regression. It's some function of the input parameters. It gives you some number coming up, and you can do linear regression. It is one way forward, but it's not probably not the most sophisticated thing you can do. But it's, it would be an emulator, I guess. Okay, so I've got this plot on the right, which I can't especially remember why that's relevant here, but it's kind of nice to come back to the Hadley cells, I suppose. So when we run all these experiments, and this again is these single parameter studies where we take the pre-industrial state, we reduce the orogeny to 50%, so we double the CO2, we add some LGM ice, we open the Panama and reverse precession. So there's a kind of 6 basic experiments there. And the kind of main point of this plot, I guess, is that you can see the scene, Southeast Asian monsoon really cares about orogeny. So when you do this experiment where you reduce the orogeny by 50%, there's a huge change in the Hadley circulation. The doubling CO2 has very little effect. So these top 3 right panels, I guess, are kind of supporting this, the Farnsworth experiment I was talking about earlier. We're coming to the same conclusions as they are, that when you're looking at those 2 variables, the orogeny and the doubled CO2, and orogeny and CO2, it's the orogeny that really matters for the Southeast Asian monsoon. Whereas conversely, when you look at the Indian summer monsoon, you get a much more complex picture, where all of these different inputs are making quite substantial changes. So doubling CO2 is really strengthening the Hadley circulation, reducing the orogeny is also weakening as before. The ice is having a stronger effect, opening the Panama, etc. Okay. So then when we want to move from these kind of 400 random simulations we've got that we've used to build an emulator, how do we progress to saying something about what happened, what might have happened in the real world? And we have kind of estimates of all these things, how they varied over time. So of course we have orbital forcing solutions in the center. So we use the Lasker orbital forcing. We have estimates of CO2 and sea level. So the CO2 we can take from the ice core records back 800,000 years. But before that, we use the STAP reconstruction, which is kind of is derived from the delta 18O signal, where it kind of decomposes an ice signal and a warming signal and infers a CO2. And that's the same for CO2. So both the CO2 and the sea level are taken from STAP. Then we make some simple statements about seaway changes. So we say the Tethys closed 15 million years ago, Panama closed 5 million years ago, and the orogeny just followed this simple 2-phase growth. So it grew from 30 to 25 million years ago, and then from 15 to 5 million years ago. So that gives us a bunch now of scalars, if you like, that vary through time that we can use and plug them into our emulator and calculate reconstructions over time. But before we look at how things vary in time, it's useful to see how much of these drivers, how much do they all contribute separately to the monsoon variability. And we can do that because for each of the inputs, so here there's an example of CO2, we can generate some kind of prior about how that varies over time. So during the Holocene, the CO2 varied 269 plus or minus 7 ppm. During the Pleistocene, 245 plus or minus 33 ppm, etc. So we've got some kind of prior statement that we can say about the CO2, and likewise for all of the parameters, because we have quantifications for all of them. So what we can do is use these priors to say how much uncertainty can they drive in the emulator itself before we even start looking at how things vary over time. And to do that, we calculate this thing called the total effect. And the total effect is the expectation of the variance that would remain if the values of all other drivers were known, which is a bit of a mouthful. It essentially means, okay, let's just imagine I know everything apart from the CO2. So I just fix all my values at something or other apart from CO2, and then I vary the CO2, and I put I vary it across my prior. So I draw from my prior, calculate a value of the monsoon that comes out by varying that prior, and I can then basically do that for all of the different parameters, and it gives you an expectation of the value of the variance in the outputs that's created by that input. So we can then see in the far right-hand column how we can quantify the relative importance of these things. So it's before we start looking at actually the specifics of how they vary, how does their relative importance vary? And for Southeast Asia, on the bottom, you can see it's basically dominated by orogeny. The variance is 94% of the variance is just coming out of the orogeny. So again, this is kind of supporting the Farnsworth conclusions. This is on the long time scales, of course, but yeah, and very huge variation in the strength of the monsoon coming out of that orogeny. But if you look at the Indian summer monsoon, the picture's much more complicated. So you still get a very important role from orogeny. It's still the dominant driver with 42% of the variance, but you're also getting significant contributions from CO2, from precession, and even from gateways and sea level. And then you can further decompose those into the different periods and kind of have a look at, where the different epochs, where is that allocation. So in the Holocene, taking a fairly simple example, because very little else is changing, it's the precession and the eccentricity that matters during the Holocene. That's not because the system's any different, it's just because things weren't changing. CO2, sea level, orogeny gateways weren't changing, so they're not having an effect, not changing significantly anyway. Okay, that's probably all I want to say about those. So then we come to the time series. So now we have got all these input time series and we can feed them into the emulator and we can generate output time series of the monsoon precipitation over the last 30 million years. So on the right hand side, we've got the emulated time series for the Indian summer monsoon, Southeast Asia monsoon. And on the left-hand side, let's say that, on the right-hand side, we have the sensitivity. So what happens if you remove, if you fix one of the parameters? So again, this is kind of a way of pulling apart how the interactions are. What are the roles of the individual parameters and how they're driving that change that we're seeing in the black curves on the left. And you can see if you go back in the first sort of 15, so from 30 million years to 15 million years ago, Southeast Asia monsoon is following orogeny. So as we know, as we've seen in this model, is dominated by orogeny until we get 15 million years ago when the Tethys close. That has quite a big effect in this model. So you can see on the top plot, the blue graph on the top right, you can see this large step change of sort of 200 millimeters of precipitation. And then once that Tethys is closed, then we kind of go back to the state where it's most of the variability, most of the change is being driven by orogeny again. And then we have this fairly stable period in the last 5 million years where not a huge amount is happening, but we are getting some reduction due to CO2, and we're getting some reduction due to ice sheets as well. And the Indian summer monsoon, again, as we could see from the total effects, it's far more complicated. There's a lot more going on. So we can still see that the signal of orogeny is quite important. So it's driving a bit of an increase in the first 5 million years. But here that's really complicated, in particular by the ice sheets. So the mid-Miocene climate up to the late Oligocene warming, where you get a big drop in the ice sheets, a big fall in sea levels. You can see the impact of those on the Indian summer monsoon. Very little effect of Tethys closure on the Indian summer monsoon. But after Tethys closure, then you get back into this renewed strengthening of orogeny as you get this more uplift of the Himalayas. But this is then competed primarily by the CO2, because CO2 is being drawn down from this time. Indian summer monsoon is sensitive to CO2, so these two things are competing, and so in the sort of overall signal you don't see this very strong increase that you do in the Southeast Asia monsoon. But what you do, the kind of final thing of note, I suppose, to mention is the Panama closure. So what happens when the Panama closes at 5 million years ago is you get this sudden strengthening of the Indian summer monsoon, and that's coming about, which goes back to the plots I showed earlier about the AMOC. So you get this once the gateway shuts, the AMOC switches on in this model. That pumps heat into the north, shifts the interhemispheric heat balance, and drives a strengthening in the Indian summer monsoon. And that's probably about everything. So what about obliquity? Worth a quick mention. So if we go back to our total effects, in this model, obliquity has very little effect. So 1% on the Indian summer monsoon over the whole period, and 1%, less than 1% of Southeast Asia, which seems surprising because, you know, models have seen variance on obliquity timescales. But we actually do see variance on obliquity timescales, but we see it through the ice sheets. So the obliquity is driving changes in sea level, and that's driving changes in the ice sheets in the model. And of course, those changes in ice sheets are driving changes in the summer monsoon. So it's kind of suggesting that a possible mechanism, at least for obliquity forcing, is through the indirect forcing of ice sheets. And then just one final note is on uncertainty. So all of this data has just been done. All of this data has been generated with one setup of the model. So we've got one bunch of parameters that are all fixed, and we vary the model. And that's not ideal practice, but sometimes it's necessary. And it's not ideal because models are very sensitive to the input parameters. So this kind of final sensitivity to present here is repeating those single parameter experiments that I talked about earlier on. So doubling CO2, halving orogeny, flipping precession to opposite phase, and adding LGM ice sheets. And first looking at the seam rainfall, you can see kind of pleasing result that the orogeny is coming out. This is a very robust conclusion of the model. Doesn't matter what you do to CO2, it doesn't matter what you do to the parameters, orogeny is always by far and away the dominant driver of any changes in the Southeast Asian monsoon, and CO2 has a very minimal effect. If you look at the Indian summer monsoon rainfall on the left, here you've got a lot more uncertainty. So again, this is kind of reflecting how this system is much more complex in the model, much more sensitive to changes in lots of in various different things. The uncertainties are large. In the case of ice sheets, even the sign of the change is unknown. So you might have noticed and been surprised that as we're growing ice sheets, we're getting a stronger Indian summer monsoon, which seems counterintuitive. You'd expect as you grow the ice sheets, you're kind of you're actually making it cold up in the north, and that would weaken the monsoon. But what's happening in the model there is it's a winter-summer contrast, and actually this precipitation increase in the model is being driven by increased winter precipitation as the winds change over coming in off the Bay of Bengal. But this is a very uncertain. I'm going the wrong way. Why? This is a very uncertain model result. So with different parameter setups, you can see that the sign of that change going in both directions. So we're not even sure of the sign of the response to ice sheets. But the other changes are all at least robust with respect to sign. That's probably all I meant to say. So then just to summarize, I don't think I actually mentioned this, but perhaps it was kind of clear from the talk in general that the Indian summer monsoon and the Southeast Asian monsoon should be treated as distinct systems. They respond very differently to their forcings. If you're looking at different drivers of monsoons, you shouldn't consider them in isolation. So these things do interact with one another, and how they interact with one another can be quite relevant for explanation. The seam is dominantly driven by orogeny, although multiple factors do contribute on short timescales, especially orbital timescales. You can see orbital signals on short timescales. But the Indian summer monsoon is far more complex, and it has significant contributions from CO2, orogeny, precession, ice sheets, and opening and closing seaways. And then finally, the scale of the CO2-driven changes is significant, and it can be expected in the Indian summer monsoon can be expected to be comparable to the variations, at least over the Holocene, but probably over the whole of the last 13 million years. Thank you. I don't know how my time was, but about right, I guess.